Hi there, Mr. Sutton here with the AB Calculus 6-9 Extra Practice Number 1 solutions on accumulation problems. On this problem, we have water being pumped out of a lake at a rate given by this R of t function. We want to know how much water is pumped from time 0 to 5. So we have the rate of pumping right here. We just need to take the integral of this thing to find the total amount of water pumped. So the integral of this from 0 to 5. So integral 0 to 5 R of t dt, which we will now do on the calculator. Just to make things a little easier to manage, I'm going to put this R of t function in my y equals under y1. And now quitting out of that, I'll do math 9. So integral from 0 to 5 of alpha trace to pull up my y1 again, and then dx. And that gives me a value of, drum roll please, 47.193. So that's going to be, let's see, choice D. For this problem, the rate at which water is sprayed on a field of vegetables is given by this R of t function. And during the time interval 0 to 4, we want to know the average rate of water flow in gallons per minute. So if I'm looking to average this function, which is what I'm doing because I want average rate of water flow, and this is the water flow function here, we need to do the integral of this thing from 0 to 4 divided by the interval length. So that's going to be 1 over 4 minus 0. That's going to give us the interval length times the integral from 0 to 4 of whatever we're trying to average, which in this case is this R of t function. And now it's time for the calculator. So the first thing I'm going to do is put this R function in y1, just to make it a little easier to maneuver this thing. And then I'll plug it into this integral. So let's see, I'm going to do fancy fraction 1 over 4 times the integral, so math 9, from 0 to 4. And then let me do alpha trace to pull up y1, and then dx. Enter. Let's see what this thing comes out to. 14.691, and that'll be gallons per minute. So that's going to be choice C. On this problem, we have a music group that expects to sell new CDs, if you remember what those were, at a rate of R of t equals this crazy function. And let's see, to the nearest 1,000, we want to know how many CDs are expected to be sold for the first 12 weeks after the release. So we have the rate at which CDs are supposedly going to be sold. We have 12 weeks, and this rate is measured in CDs per week. So in order to find out how many we actually will end up selling, or at least we expect to sell, we need the integral of this thing over the interval from 0 to 12. So I'm going to do integral from 0 to 12 of R of t dt, and let me put that in the calculator. I'll begin by putting this in my y1 just to make it a little easier to move around. And now I have math 9 for integral, 0 to 12, and alpha trace to get my y1, dx. Enter. That gives us about 130,000 if we round that off to the nearest 1,000. Although actually, no, nearest 1,000 would be 127,000. I was doing 10,000s. So 127,000 CDs, that would be choice D. For this problem, which is a no calculator problem, the rate in calories per minute in which a person using an exercise machine burns calories is modeled by the F function, which is shown above right here. Now this is kind of interesting because from 0 to 4, which we can see on this graph, it's kind of curvy. This is the function, this polynomial is the actual function. Whereas from 4 to 24, the rest of this graph, this is a piecewise linear kind of graph that we have to read things off the graph for. So our first part of the problem, they want f prime of 22 with units of measure. So we want the slope of the f graph at t equals 22, so right here. Since this is on a line, if we find the slope of this line, then we have actually found the instantaneous rate of change of our function at 22. So let's see, just looking at the numbers on the graph, we are going down 12 from 15 to 3. So that's negative 12 for the change in y and positive 4 for the change in x. So our slope then is negative 12 over 4, which if you wanted to, you could reduce to negative 3. But either way, you need units of measure. Since the original graph was calories per minute, and we're finding how this is changing over time, this will then be calories per minute squared, When you take the derivative of something, you divide it by whatever the input units is, in this case dividing by minutes, minutes squared. On this problem, they want to know on the time interval from 0 to 24, at what time is f increasing at its greatest rate? So just to translate what they're asking for here, if we're asking where f is increasing, we're asking about f prime, so we want the highest value of f prime. We want to find the absolute max on this interval for f prime. So this is going to be a little bit tricky, but let's at least start by breaking down where we should be looking. Let's only look in the places where f is actually increasing. So for example, f prime, the slope of f, is only positive on the interval from 0 to 4, and also on the interval from 12 to 9. Everywhere else it's either constant or decreasing. So let's look at 0 to 4 first. That's the polynomial piece. That one's going to be a little trickier, so let's just get that one out of the way. So for this one, we actually need to find what f prime looks like as a function. We can do that because they gave us f of t right here. So f prime, taking my power rule derivative, that's going to be negative 3/4 t squared plus, let's see, these 2's cancel, so that's 3t. And now I need to figure out the maximum value for this function right here. To do that, I'm going to need to find its derivative. So that's f double prime of t I'm finding now. That's going to be negative 3/2 t if I do 6 over 4 there. So negative 3/2 t plus 3. And I now need to find critical values for the derivative of f prime. So critical values here. And the only ones I'm going to find are ones where this thing equals 0. So subtracting 3 and then multiplying by negative 2/3. 2/3 times 3, or negative 2/3 times negative 3 actually. Same thing though. That's going to come out to positive 2 for my t value. So this is our critical value. Is it a max or min? We could do sign analysis with the first derivative, or we could take another derivative and just use the second derivative test. I'm going to go for the second derivative because that's pretty easy. F triple prime, if that's possible here, is just going to be negative 3/2. Now significantly, this is negative everywhere, including the value at t equals 2. So that means, since we're dealing with a concave down situation, this is going to be a max that we just found at t equals 2. All right, so what is the actual value at t equals 2 of the f function, or the f prime function? Because we may have to compare it to whatever f prime value we get for this other interval later on. So to figure this out, let's plug 2 back into f prime. And that's going to tell us what value we have to beat with that other interval. So that's going to be negative 3/4 times 2 squared plus 3 times 2. And we are going to simplify this so we can compare it more easily to other values we get. This is negative 3/4 of 4, which isn't too bad. That's just negative 3. Plus 6 comes out to positive 3. So that's the value to beat for f prime. Let's see if we can do better in the interval from 12 to 16. So for 12 to 16, it's a little bit easier because this is just a line. So that means the value of f prime, the highest value, the only value, is going to be whatever the slope of this line is. We're going up from 9 to 15, so up 6, to the right 4. So we have 6/4 for the slope on this thing, for the f prime, which is 3/2. Significantly, this is less than the only other max candidate we have in this problem, less than 3. Therefore, f is increasing. F prime has its greatest value at t equals 2 minutes. For part C, we want to find the total number of calories burned over the interval from 6 to 18 minutes. So if I'm trying to find the total calories burned based on a graph of calories per minute, I need to integrate this function here. And this is all the changes in calories. So integrating this will give me the total calories burned. So I need the integral from 6 to 18 of f of t dt. All right, I might actually get a point for writing that, but now I have to calculate it. So I'm going to use basic geometry to figure out the area under the curve, which is what we're really doing when we integrate a function. So I have a few shapes that I'm dealing with here. From 6 to 12, I've just got a rectangle. From 12 to 16, I've got this trapezoid here. And then from 16 to 18, about halfway through here, I've got another rectangle. So for the rectangle, the first rectangle, we have a base of 6 times a height of 9. So 6 times 9. Plus, now for the trapezoid, I have a base of 9 plus a base of 15 divided by 2 times a height of 4. And then finally for this rectangle, I have a base of 2 times a height of 15. And if I were to stick units on the end of this thing and call it a day, I'd actually be done with the problem. But if you just can't leave well enough alone and need to simplify this, let's do that. 6 times 9 is 54. And then let's see, 9 plus 15 over 2, that's the average of 9 and 15. That's 12 times 4 is 48. 2 times 15 is 30. Adding these together, let's see, this is going to be, this is 90 plus 12. That's 102 plus 30 is 132 calories. I think I'd burn some calories just adding those together. For part D, the setting on the machine is now changed so that the person burns f of t plus c calories per minute. So this whole graph essentially is getting shifted by some amount either up or down. So for this setting, we want to find c so that an average of 15 calories per minute is burned during the time interval 6 to 18. Well, if I'm talking about average value, I'm going to set this up like an average value problem. So let me write an expression for the average value from 6 to 18 of this f of t plus c function. Average value, that's going to be 1 over the interval, so 1 over 18 minus 6, times the integral from 6 to 18 of this stuff, and then all of that should come out to a value they said of 15. All right, well, let's go a little further. So I'm going to simplify this expression a little bit and move a few things around so I can solve this a little bit more easily. So let's see here. This is really 1 over 12. And I'm going to split this integral up. And you'll see why I'm doing this in a minute. So I'm going to have the integral from 6 to 18 of f of t dt plus the integral from 6 to 18 of c dt. And all of this still equals 15. So 1 over 12 and split up the integral. Now here's why I did this. Integral from 6 to 18 of f of t dt. We already know what that is. We calculated that in part C, and maybe like me, you actually simplified it in part C. If not, this would be a good time to simplify it. So we already know what this is, and this next thing here, this is just a constant that we're integrating from 6 to 18, so that's not going to be too bad. Let's do this first integral first. Remember, this was 132 calories. So we have 1/12 times 132 calories. Again, this was from part C. And over here, I've essentially got a rectangle from 6 to 18, so we have a base of 12 and a height of c. So the area of that rectangle is just going to be 12c. So I've got 132 plus 12c, and all of this should come out to 15. At this point, I can actually start solving for c because there's no more fancy calculus notation left here. I'll start by multiplying both sides by 12. 15 times 12 I happen to know is 180. And now let's subtract 132. That gives me 48. 48 divided by the 12 here gives me a c value of 4. On this problem, to get the setup here, a metal wire of length 8 centimeters is heated at one end, and this table here is giving selected values of our temperature, which we're calling T of x, in degrees Celsius of our wire, x centimeters from the heated end. So basically, you heat up one end of the wire, and as you get further and further and further away from the heated end, obviously your temperature is going down because some of that heat is being lost. Why? Well, because science. We'll let somebody else answer that. So the function t, they're also telling us, is decreasing and twice differentiable, which will be important. All right, so for our first part, part A, they want us to estimate t prime of 7, and then show our work and include the units. So to estimate the instantaneous rate of change of our t function at time 7, I'm going to find the average rate of change over an interval that includes 7 here. And I said time 7. I really meant distance 7. This is kind of a weird setup with distance instead of time being the input value. So I'm going to choose the interval from 6 to 8. That's the smallest interval that includes 7. Any interval on here that includes 7 would work, but 6 to 8 is going to give us the best answer. So I've got t of 8 minus t of 6 over 8 minus 6. So that's 55 minus 62 over 8 minus 6. And let's see, that reduces to, this is negative 7 over 2, so negative 3.5. And that is going to be in units of degrees Celsius per centimeter. That's the rate at which our temperature is changing with respect to distance. For part B, they want us to write an integral expression in terms of T of x for the average temperature of the wire, and then estimate it using a trapezoidal sum with 4 subintervals. All right, so let's get our integral first. So for average temperature, we need 1 over the length of the integral. So that's, let's see, since we're doing it across this whole distance here, that's going to be 1 over 8 minus 0 times the integral from 0 to 8, starting point to stopping point, of, well, what are we finding the average value for? We're finding the average value of the temperature of the wire, which is expressed by T of x. So we're going to put T of x dx in here. And now we're actually going to go ahead and estimate this thing. So I'm going to start with 1/8 outside, a big parentheses, and inside, let me do my trapezoidal sum now. So I'm going to have a base of 100 plus 93 over 2 times a height of 1. And then I've got 93 plus 70 over 2 times a height of 4. Then 70 plus 62 over 2 times a height of 1. And finally, 62 plus 55 over 2 times a height of 2. If you wanted to be done with the problem, which I would recommend, just put units on the end here and call it a day. What are the units on this one? Well, since this is average temperature, it's going to have the same units as normal temperature, which is to say degrees Celsius. If you just can't leave well enough alone, we could keep going, and this was a calculator problem, so you could actually plug this into your calculator. I'll do that now just for the sake of argument here. Okay, so I've plugged this whole long string of things in my calculator. I used alpha y equals, Francie fraction, a whole bunch here. This comes out to approximately, well, this crazy number. I'm going to turn that into a decimal and estimate it here. So decimal value of that is going to be about 75.688. And again, that's degrees Celsius. For this part of the problem, they want us to find the integral from 0 to 8 of t prime of x dx with units of measure. Now, before you freak out here, don't worry, because even though we don't know what the t prime function actually does, we do know the antiderivative of t prime. It's just t. So this is just evaluating t from 0 to 8, t of x from 0 to 8. This is t of 8 minus t of 0. Well, what's t of 8? According to our table, that's 55. T of 0 was 100, so we have 55 minus 100, which, if you wanted to simplify it, is negative 45. What are the units going to be on this? Well, we're taking the rate of change of a temperature over distance here and integrating that. So that means we're essentially multiplying by the input units here, which is centimeters. So that just gives us temperature back. This is just the temperature. This is going to be negative 45 degrees Celsius. Now, what does this actually mean? The meaning of integral of 0 to 8 of t prime. So this is the total change in temperature in degrees Celsius from 0 to 8 centimeters. And if you wanted to actually spell out what your answer means, it means that as you go from 0 to 8 centimeters away from the heated end of this wire, your temperature is dropping 45 degrees Celsius. For this last part of the problem, are the data in the table consistent with the assertion that t double prime of x is greater than 0 for all x on the interval 0 to 8? Explain your answer. Now this one is actually a pretty tricky one because they're asking about t double prime of x when they've really only given us a little bit of information about t of x. Well, t double prime of x, if that's positive, that's one way of reading that is to say that t prime of x is increasing across this whole interval. So we could try to work with that. The only other way to read this is that t of x itself is concave up across this whole interval, which is awfully tough to figure out based on what they've given us in the table here, because, I mean, for one thing, these aren't even going by ones. We have uneven interval lengths here. So let's try to work with t prime of x. So we have to get a couple sample values of t prime of x and see if they're actually going up. How can we pinpoint what t prime of x is? Well, the only way to do that using a table is if we use the mean value theorem. Because this function here, t, is twice differentiable, they said it's twice differentiable, that means that our mean value theorem actually applies. So if we can figure out the average rate of change over a few of these intervals, that's going to tell us what some of the instantaneous rates of change are across these intervals as well. So let's do an easy one here. Let's do some low-hanging fruit. Let's do the interval from 0 to 1. So I'm going to find a rock from 0 to 1. That's going to be, let's see here, 93 minus 100 over 1 minus 0, which is just simply negative 7. So since we have differentiability, and we just found an a rock of negative 7, that means that on the interval 0 to 1, we have some C1 value at which we have a t prime of negative 7. So we're guaranteed there's an exact value of negative 7 for t prime somewhere on this first interval. We don't know where, but it's somewhere on there, and that's really all we're going to get out of that. All right, let me find another average rate of change. Now, I could do the one from 1 to 5, but that would require a little bit more simplifying. Let me do 5 to 6, because that's also a distance of 1, so that one's going to be pretty easy. So a rock from 5 to 6, that's going to be 62 minus 70 over 6 minus 5. This is just negative 8 over 1, which is negative 8. That guarantees by the MVT that t prime equals negative 8 for some other value on the interval from 5 to 6. So let's take stock of what we've learned here. At this point, so earlier on in the function, I guess you could say, we had a t prime of negative 7. Later on, we had a t prime of negative 8. That means t prime decreased. Well, that wouldn't happen if t double prime was positive. If t double prime was positive everywhere, then this value should go up from negative 7, not down. So since t prime decreases somewhere on the interval from 0 to 6, it has to get from negative 7 to negative 8, that means that it's not true that t double prime is positive for all x on 0 to 8.